Welcome everyone. Today, we're going to explore the topic of pressurization units in chilled water systems, with a focus on their purpose, need, and how to select them effectively. This is the first slide, serving as our overview. We'll be explaining these concepts with formulas and real-world examples, making it easier to understand for junior and new HVAC design engineers. So, let's get started and see how these units help keep our systems running smoothly. Let's start by looking at the key design inputs that we need to gather right at the beginning. These inputs are crucial because they set the foundation for all our engineering calculations. First, we have the building height, which is measured from the ground up to the highest point. In our example, that's 42 meters. This helps us understand the vertical constraints of the site. Next, the system water volume, which is 30,000 liters in this case. Knowing this volume is essential for designing the system capacity and ensuring it operates efficiently. Then, we consider the CHW temperature range, which here is from 6 degrees C to 14 degrees C. These temperatures are critical because they influence how we size the system components and control strategies. Another important parameter is the water expansion coefficient, which is 0.0003 per degrees C. This tells us how much the water volume expands with temperature changes, a key factor for safety and system integrity. We also need to account for a safety pressure margin. In our example, that's 0.5 bar to ensure the system can handle pressure fluctuations safely. The location of the system unit is specified as the basement, which affects access, installation, and maintenance considerations. Finally, we choose the design code, such as ASHRAE or CIBSE, to ensure our design complies with recognized standards and best practices. Before we get into the detailed calculations, it's clear that collecting this site-specific data is mandatory. It helps us understand the physical constraints of the building, the operating conditions, and the relevant standards to follow. By doing so, we ensure that our design is both safe and optimized for the actual site conditions. Let's take a closer look at static pressure calculation. Here, P static represents the static pressure in bars, and H stands for the vertical height in meters. Now, the key idea is that static pressure is caused purely by the height of the water column. A handy rule of thumb is that every 10 meters of water column produces about 1 bar of pressure. So, if we have a building that's 42 meters tall, we can estimate the static pressure by dividing 42 by 10, which gives us 4.2 bar. This means that to push water all the way to the top of a 42-meter high building, we need at least 4.2 bars of static pressure. It's important to remember, because this pressure has to be overcome by the system's pump or other means to ensure water reaches the highest point. Understanding this concept helps us design effective water systems, ensuring enough pressure is available for proper flow throughout the entire building. Let's talk about the minimum operating pressure, or PMIN, for this system. The result we've calculated is 4.7 bar. Now, you might wonder, how do we arrive at that number? Well, it's based on the formula Pmin equals P static plus PS. In this case, P static is the static pressure, and PS is the safety margin that we add on top. It's important to note that the minimum operating pressure isn't just the static pressure alone. We add a safety margin, usually about 0.5 bar, to prevent air from entering the system and to ensure the pumps have enough suction pressure to operate effectively. This safety margin is a standard practice in HVAC systems, so it's quite reliable. So, by adding that 0.5 bar to our static pressure, we determine that the minimum operating pressure should be around 4.7 bar. This ensures system stability, efficiency, and safety, connecting directly to our overall goal of designing a reliable and effective HVAC system. Now let's look at the maximum operating pressure, or PMAX. In this case, the result is 6.2 bar. To understand how we arrived at this number, we use the simple formula. Pmax equals Pmin plus 1.5. In our example, Pmin is 4.7 bar, so when we add 1.5, we get a Pmax of 6.2 bar. The maximum operating pressure is really important because it defines the upper safe pressure limit for the system. It depends on several factors, including the pressure rating of the pipes, the design of the expansion vessel, and the safety valve settings. Typically, we maintain a control band of about 1 to 1.5 bar above the minimum pressure to ensure safe operation without risking damage or failure. In this case, the calculated maximum pressure of 6.2 bar helps us stay within those safe limits and keep the system functioning reliably. Let's take a closer look at the system expansion volume, or VE. In this example, the result comes out to 72 liters. To understand how we arrive at this number, we start with the formula VE equals V's times beta times delta T here. V's represents the system water volume, which in our calculation is 30,000 times 0.0003 times 8. Now, delta T is the temperature difference, which in this case is 14 minus 6, giving us 8 degrees Celsius. The key point to remember is that water expands when its temperature increases. Even a small temperature change, like these 8 degrees, can lead to a significant expansion volume, especially when dealing with a large quantity of water in the system. Using the expansion coefficient of water and this temperature difference, we calculate the total expansion volume as 72 liters. This is crucial because it shows how temperature fluctuations can impact the system's volume and potentially influence system design and safety considerations. So, understanding these calculations helps us better manage and predict system behavior under different thermal conditions. Let's take a closer look at the expansion vessel size, or VTANK, that we've selected for this system. We've chosen a 300-liter vessel, but let's understand how we arrived at that number. First, the calculation for the required vessel volume, VTank, is based on the ratio of maximum to minimum pressure in the system. The formula is VTank equals V divided by the pressure ratio minus 1. In this case, V, the expansion volume, is 72 liters, and the pressure ratio is calculated from the pressures of 6.2 bar maximum and 4.7 bar minimum. When we plug those numbers in, V-tank comes out to approximately 225 liters. This tells us that, theoretically, a 225-liter vessel would do the job perfectly to accommodate the expansion and contraction of water with temperature changes. However, since expansion vessels are available in standard sizes, we look at common options. Here, we see that a 300-liter vessel is a standard size that comfortably exceeds our calculated need. Choosing this size ensures we have enough capacity, providing a safety margin and simplifying procurement. So the key takeaway is that the vessel size is calculated based on the pressure ratio, but practical considerations like standard sizes influence the final selection. This ensures reliable operation and easy maintenance, which ties back into our overall goal of designing a safe, efficient, and manageable system. Let's take a closer look at the pressurization pump flow rate, or QPU. We've selected a flow rate of 0.5 cubic meters per hour. To understand how we arrived at this, we used a simple calculation. QPU equals 1.5% of the total system volume, which in our case is 30,000 liters. Multiplying 30,000 liters by 0.015, or 1.5%, gives us 450 liters per hour. Now, it's important to note that the formula we used, QPU equals 1.5% times V's, reflects industry standards. Typically, this value ranges from about 1 to 2% of the system volume per hour. The purpose of the pressurization pump isn't to circulate fluid throughout the system. It's primarily there to compensate for small leakages and keep the pressure stable. Choosing a flow rate within this industry range ensures the system remains reliable without oversizing the pump. So, by selecting 1.5%, or 0.5 cubic meters per hour, we're aligning with best practices to maintain system integrity efficiently. This approach helps us balance performance and cost, ensuring the system functions smoothly over time. Now let's look at the pressurization pump head, or HPU. We've selected a head of 65 meters for this system. To clarify, The calculation here is based on the maximum pressure the system will experience. We use the formula HPU equals Pmax times 10, which helps us determine the necessary pump head. Since we know that approximately 1 bar of pressure equals 10 meters of water column, multiplying the maximum pressure in bars by 10 gives us the required head in meters. In this case, with a maximum pressure of around 6.2 bars, multiplying that by 10 results in 62 meters. To ensure safe operation and account for any variations, we select a pump with a head of 65 meters. This way, the pump can reliably overcome the maximum system pressure and maintain proper system performance. This concept is crucial because the pump head must be sufficient to handle the highest pressure conditions the system will face, ensuring stability and safety. In this final slide, I want to give you a clear summary of the pressurization unit selection. First, the system pressure is maintained within a range of 4.7 to 6.2 bar, ensuring reliable operation without overpressurizing the system. The expansion vessel, which is 300 liters, plays a crucial role in accommodating thermal expansion, preventing pressure spikes as the system heats up. The pump we've chosen has a flow rate of 0.5 cubic meters per hour, and it provides a head of 65 meters, which means it's capable of maintaining consistent pressure throughout the system, even at higher elevations or longer pipe runs. We've also included a configuration with one pump working and another on standby. This setup boosts system reliability. If the primary pump needs maintenance or fails, the standby pump can seamlessly take over, minimizing downtime. Overall, these specifications are carefully selected to ensure the system remains stable, efficient, and reliable, supporting the overall theme of designing robust pressurization solutions. Let's go over some practical design notes to ensure your chilled water system operates smoothly and reliably. First, it's important to use a diaphragm-type expansion vessel. This type helps accommodate pressure changes effectively and maintains system stability. Next, including a safety valve set at Pmax plus 10% is crucial. This valve acts as a safeguard, preventing overpressure conditions that could damage the system. You'll also want to install auto air vents at the high points of the system. These vents are essential for removing trapped air, which can cause noise, inefficiency, or even damage over time. Connecting the pressure unit near the chilled water pump suction line is a best practice. Doing so ensures accurate pressure regulation and easier maintenance. Overall, proper placement and component selection, like these, contribute significantly to a smooth, reliable, and long-lasting chilled water system operation. These practical design considerations are key to achieving optimal performance and system longevity. Now, let's take a closer look at the pressure maintenance logic. Essentially, once the system reaches the required static head and it's stabilized at our predetermined set point, the control circuit will then shut off the pump cycle. This is a crucial step to prevent overpressurization, which can cause damage or inefficiency. So, when the pressure hits our set point, the pump stops, ensuring we maintain optimal pressure without risking system integrity. On the flip side, if the pressure drops below the minimum static head requirement, say, due to some demand change or minor leak, the control system kicks in again. It detects this decrease and activates the duty pump to restore both volume and pressure back to the ideal levels. This logic ensures a continuous balance. When the pressure is sufficient, the pump is off, saving energy and reducing wear. When it drops, the pump gets back to work automatically. This cycle plays a vital role in maintaining system stability and efficiency, tying directly into the overall theme of effective pressure regulation in our system. Let's take a closer look at the safety response logic. When there's a critical drop in pressure, the system is designed to respond immediately. It triggers a system-wide alarm, which not only alerts the facility management team, but can also interlock the main chiller plants to ensure safety. This rapid response helps prevent potential damage or failure. On the other hand, if the system encounters an overpressure situation, perhaps due to thermal expansion or a mechanical fault. The safety relief valve kicks in automatically. Its job is to discharge excess fluid safely, preventing any pressure buildup that could cause damage or hazards. Both of these mechanisms are essential for maintaining safe operation. They are key parts of our overall safety strategy, ensuring that any abnormal pressure condition is handled swiftly and effectively to protect both personnel and equipment. Now, let's take a closer look at some of the primary hydraulic accessories that play a crucial role in our system. First, we have the analog visual indicator, which provides real-time pressure readings. This is essential for site monitoring and manual verification, allowing us to keep an eye on system performance at a glance. It helps us quickly identify any pressure anomalies that might need attention. Next, there's the pressure gauge. Think of it as our system's pressure thermometer. It gives us an accurate, immediate reading of the pressure within the system, helping us maintain safe operating conditions. Moving on, we have the pressure relief valve. This is a vital safety device designed to protect the entire system. If pressure exceeds a set limit, the valve automatically releases fluid to prevent damage or failure. It's like a safety valve that ensures system integrity under pressure spikes. Finally, there's the expansion vessel, specifically of the diaphragm type. This component is sized to accommodate volumetric thermal changes, that is, when the fluid heats up and expands. It maintains a constant static pressure within the network, preventing pressure fluctuations that could harm the system or reduce efficiency. All these accessories work together to ensure our hydraulic system runs smoothly, safely, and efficiently, aligning perfectly with our goal of reliable and effective site management. Now, let's look at the performance objectives of our system. First, protection against air ingress and pressure loss is critical. If air gets into the system or pressure drops unexpectedly, it can disrupt operation and reduce efficiency. So our design includes safeguards to prevent that from happening. Next, controlled water expansion is important to accommodate temperature changes without causing stress or damage to the system. This ensures longevity and consistent performance. Maintaining adequate system pressure is also vital. Proper pressure levels help ensure that the chilled water circulates effectively and that the entire HVAC system operates smoothly. Overall, I want to highlight that our proposed design meets all relevant industry standards, which gives us confidence in its reliability. The pressurization unit is specifically designed to keep the system safe, stable, and continuously operational. By doing so, it guarantees that the chilled water system runs efficiently and without interruption, supporting the overall performance of the HVAC system. Now, it's important to remember that actual system requirements can vary quite a bit depending on several factors. These include the final selection of equipment, site-specific conditions, how the system is configured, and the local authority regulations that apply. What we're emphasizing here is that our design notes are based on standard HVAC engineering practices. These are proven methods and typical assumptions used in the industry to guide our planning. However, keep in mind that these are preliminary estimates, and actual conditions on site may lead to adjustments. This particular slide focuses on the chilled water system design note, which is a critical component of the HVAC system. It's essential to understand that while these guidelines provide a solid starting point, they need to be flexible enough to accommodate real-world variations. Overall, the key takeaway is that our design is a well-informed foundation, but it must be adaptable to final project details and regulatory requirements. Thanks so much for your attention today. I truly appreciate you taking the time to be here. If you have any questions, comments, or if you'd like to discuss anything further, please feel free to share. Your feedback and insights are very welcome. Once again, thank you for your time and engagement throughout this presentation. And with that, I'll just say thank you and encourage you to stay connected.